just talk in a different voice that doesn't sound like you, with a different accent. Okay, so a quick recap of formula. This was from the last page of last lesson's notes, but I said would be a good warm-up today instead. Recap of formula. Write down the formula used to find any term in an arithmetic sequence. So if you're not sure what it's asking, the U of n. Does anyone want to just say out loud what they think it starts with? Yeah. U of 1 plus good. D, that's the one. These are all just from the formula booklet. Just a little recap. So you can be looking at your formula booklet, no problem, because that's what you're allowed to do in your tests and exams. Write down the formula used to find the sum of an arithmetic sequence if you don't know the last term. If you don't know the last term, it's the long one. Yeah. Yeah.
Plus n subtract 1 d.
Yeah. They look quite similar, don't they? Because that's the one with the U of n formula subbed in. So U of 1 plus, oh, I'm going to wait the next one. So this is the same as the short one, but with that one subbed in for the U of n. Let me just scroll down a bit because it gets a bit funny.
No.
That's okay. You tell me when, if it's going down too fast, that's no problem. Write down the formula used to find the sum. If you do know the last term in the sequence, S of n equals
n over 2.
Yeah, good.
U1 plus un.
Yeah, good. U1 plus U of n, and U of n is the last term. So if you want to make a note, you can say U of n is the last term again, just if that helps. Letting some people write that down. Let's quickly save that. These, as I said, these are all just coming from the formula booklet. So, okay. Yeah, if you have questions about them. A little recap on the formulas. It's very formula intense, this topic. Write down the formula used to find any term in a geometric sequence. So the U of n, this was back from L2, I think.
U1
Yep.
R
Yep.
n negative subtract 1.
Yeah. So that might seem like that was like months ago that you learned about that one. So geometric sequences is the first term multiplied by the common ratio raised to the power of n minus 1. That's the way they'll write it in the formula booklet. Common ratio is what you're multiplying by each time.
No, that's so today's day 2, but I'm actually finding
Yep, today's day 2.
So when I
Yep, that's right, yeah, correct. And every other lesson we're in room 2.
every other lesson just
Yep.
name it. So no more room 3.
No
No
room.
more IB3.
Yeah, no, we're always room 2, except day 2 we're always in this room. Because there's economics, Miss McMahon's economics class are in room 2, and they're reasonably big, so they might need that room still. I haven't proposed swapping with her. I might ask her at some point if she ever prefers this room. But she's got a pretty big class in there. So she might prefer that one. So I'll ask her though, in case she does prefer this room. This is kind of nice to have a change here and there, just to break it up. What's number 5? Yeah, what numerical values can n, the position of any term, take?
Anything but 0.
What number values can n be? Like, that's the position. Can you get a negative 4th term?
No. So anything, so what do you call them, natural numbers?
Yeah, natural numbers. That sounds good, yeah. So natural numbers, or positive integers, or natural numbers. Positive integers, which the symbol for that would be Z plus. Z plus is a symbol for positive integers. We could say or natural numbers, which is the symbol N. Positive integers is a bit safer to say, because some books think that 0 is a natural number, and some books say that 0 is not a natural number. But both would be fine. We know what you mean. Basically, positive whole numbers. Like, you can't get 5.4 as an answer for n. It's not possible to get a 5.4th term in a sequence. What's the difference between a sequence and a series? Series. Je ne sais pas, yeah. So series means kind of sum. So that you could add that, just say that if you want that kind of differentiation. Sequence is just a regular sequence, nothing much to say. A series is a sum of n terms in a sequence. Of n terms in a sequence. That would be, if you've got a different explanation, you would have in place that sequence. So specifically, series refers to sum. So some formulas are called series. So it's a little recap on the stuff we've done so far. Now on to, okay, we've done U of n for arithmetic and geometric. We've done the sum formulas for arithmetic. So you've probably guessed today's the sum formulas for geometric, which again are just in your formula booklet. Yeah, so the formula is just going to be in your sum formula booklet, not a big deal. A series, as you've probably guessed already, is the sum of the terms in a sequence. So for a geometric sequence, this series would be, that's the sequence, and the series would be this, when you're adding them all together. So that's the sequence, that's the series. Out of interest, what's the U of 1 in that sequence?
G.
Yeah, good. And what's the R in that sequence?
That has the.
Yeah, good. Exactly 2. Because it's exactly what you're multiplying by each time. So we're doubling each time. So U of 1, that looks like an R, sorry. That's U of 1. U of 1 is 2, R is 2. Just reminding us about geometric sequences. You're multiplying each time to get the next term. Yes, Lauren.
I have a question that's not quite relevant right now, but how do you find the number of terms in a sequence?
Number of terms in a sequence. Quite often, if it was a arithmetic one, if they tell you what the last term is, then you can use the U of n formula back to here. I would suggest if it's arithmetic, use the U of n formula. And imagine you know what the last term is, so you can put that in. Maybe you know the first term, and maybe you know the common difference. And then you'd have to solve for n.
That makes sense.
Yeah, so quite often, sometimes you might find that there's ones where you have to, you might know other things. Maybe you know everything here and you have to solve for d. So it's a lot of algebra and rearranging and solving going on for d. And that's if it was arithmetic. If it was geometric, you would do the same thing but with a geometric formula. So if it was a geometric one, you would plug in the last term. If it was geometric, last term, you plug in the U of 1 and the R. You'd probably have to use logs to solve for n. So that could happen. So remember there were some where we had tricky ones where there were logs to solve for n. So we can generalize, can't read my own writing. You can generalize what the sum of a geometric series looks like algebraically. This is an awkward formula in your formula booklet. Does anyone happen to see it in their formula booklet or on the first page of their booklet? What the formula for the sum of a geometric is? It's a fraction. A little clue is it's a fraction. Just so you know you've seen it.
Right there too.
Yeah, I tend to use the first one. So let's use the first one.
It's like U of 1.
Yep.
Bracket R to the power of n.
Yep.
Minus 1.
All over.
R minus 1.
Okay. So Grace has pointed out, she's had a look at the earlier page in your unit booklet, is like where I've taken a snip of the formulas from the formula booklet. There's 2 versions. There's this one, and they happen to give, that's meant to be U of 1 right next to the brackets. It's just the way I drew it came out a bit funny. So maybe I'll redraw it. So it was U of 1, R to the power of n minus 1, all over R minus 1. So remember, if you forget them, have a look in your formula booklet, because they're all in there. This is an important formula, so we'll circle that. And Grace has pointed out that there's 2 versions of it in the formula booklet. And you can use either version, they're the same thing, it's just one's a slightly rearranged version. Like one of them has 1 minus R on the bottom, and it has, what does it have on the top? It's very similar, they just rearrange it. Yeah, it's just swapped around kind of, isn't it? 1 minus R to the n minus 1 probably, and 1 minus R on the bottom. I'm not sure why the IBO has decided to give you both versions. because they're really just the same formula, just one's rearranged. I don't know why they've given you both. Maybe it's because some countries in particular really favour the other rearranged version, and to make sure they're being international, they've said, okay, let's give both. But they're the same formula. So I tend to say just look at the first one. The first one's fine. I've never seen a case where you had to use the second one, because they've got the same things. They've got the R to the N, they've got the U of 1, the R's. It's the same
I
variable.
was talking about the finite and infinite compared to two different things, so we're talking about the finite here.
Yeah, this is the finite one, yeah. The infinite one is actually the next lesson's topic.
Okay.
Yeah, so the finite one, yeah. So this is, that's right, a good point. Grace has pointed out that in the formula booklet, they call this for a finite series, isn't it? For a finite series, meaning something that ends. Next lesson we learn about infinite series, infinite geometric series that go on forever and ever and ever. Kind of like the Gauss problem when it was going halfway there and halfway there again, halfway and halfway. That's an infinite series.
So Grace, Lauren, and I will have all the notes. Will we fit in?
When's your last day? Is it Wednesday?
Wednesday.
You're definitely not here on Thursday.
No.
So you might miss the applications lesson. But I could kind of have it ready for you. I can give you the blank notes. And it's nothing new, it's just word problems.
Okay, and
Yeah.
we'll just do that.
Yeah, and you can see it as practice, and the video, you can just look at the video and skip ahead to check your own answers if you want. You could probably almost do it yourself, and it won't be that long, because there's heaps of applications in the textbook anyway. And as I said, the maths isn't different, it's just decoding what is it asking you to do. Like when they say in an applications question, you keep an eye out for the word total. If they say, what's the total amount? Normally that means they want the sum. If they say, how much would they earn in week 5? That means find the U of N. So it's really just the same maths as the previous lessons, just decoding what the questions are asking when it's a real life question. Okay, so back to here. Here's the wacky formula for geometric series. Why do you think the formula booklet includes R cannot equal 1 on the side? So on the side, in the formula booklet, they've got something that sometimes confuses students. They on the side, in the formula booklet, say R is not allowed to equal 1. So why might be a problem if R was equal to 1?
Then it'll be 0.
Yeah, the
And
denominator.
with 0
Exactly, yeah. So it's because if you had R is equal to 1, you would have a 0 denominator. And remember in maths, we're not able to divide by 0 in maths. It's a non-allowed mathematical operation. So he's back again. So, that's what. If R equals 1, then the denominator becomes 0. Becomes 0. 0. And only so just a little explanation. So I mentioned that because sometimes students get a bit thrown when they see that in the formula booklet. And they're like, what's that all about? They're just being very clear in saying that if you did that, the formula doesn't work anymore. If R equals 1, that formula is not valid anymore. Now let's go on to some problems. Now we're just doing a few practicey ones. Right here, I see. So little practice problem down here. Nice straightforward one where we're just throwing things into the formula. Find the sum of 2 plus 6 plus 18 plus 54 to 12 terms. They want us to just throw these things into that formula. So remember, I like to write my little list. If you like to do it, you're welcome to. I like to write out U of 1, I like to write out R, I like to write out N, and also say what they're looking for. It just helps me to relax before I start doing too much thinking. What's our U of 1? 2. 2. What's our R? 3. It is, I was about to say 4. Embarrassing. Yeah, you're right, because it's times 3, times 3, times 3. If ever you can't see it, you can go like 6 divided by 2, 18 divided by 6. That divides by that. Ratio is 3. Common ratio is 3. What is our N? 12. They gave us that in the question. And they want us to find the sum. So they want us to find S of N. You could write S of 12. I sometimes like to write what we're looking for as well. It just helps me plan out what I'm doing for the day. And then we throw it into that wacky formula. So So it's S of 12, most straightforward one. Our numerator is 2. Notice its brackets are, thank you, U of 1, brackets r to the power of n. So 3 to the power of 12, we've got to put into the calculator. Minus 1 over r minus 1, 3 minus 1. This is when on your calculators you'll probably want to use the fraction button, like you know how you can do this thing. Remember, how do you make that happen again on your calculators?
Alpha, y.
Good, alpha y equals, yeah. So feel free to write that if you want. Alpha, that's the alpha button, and the y equals button. So many things can go wrong if people don't use the nice fraction button. Alpha y equals to make a lovely fraction, and then we just write out what our number is.
Alpha. Don't you have a sister? I have two sisters.
An older one as well? Oh,
What's your sister's name? Well, you recently know you really do that.
do you get something in the 500,000s?
Yeah.
Good.
531,440.
That's right, yeah.
It doesn't make sense because you multiply by 2, then you divide it by 2. You just leave it how it was. Because when you get these in the
Ah,
brackets, you multiply by 2 and you divide it by 2.
well noted, yeah.
Oh,
So
they
those
cancel
two,
out.
they're going to cancel out. Yeah, so overall this is 3 to the 12 minus 1. Yeah, so it just turned out that they kind of did. That's interesting, in that particular example. So that's your answer. So if you're asked to add up the first 12 terms in this geometric sequence, you get a massive number. So doing that manually would be a pain. That's why these formulas are nice. They save you having to do something like that manually. These kind of things, there's a lot of applications in finance. If you end up working in Bermuda in the finance industry, you deal with particularly geometric series a lot and geometric sequences. Example, find a formula for, so find a formula just means your answer is going to be an expression or an equation. Find a formula for S of n for this thingy to n terms. So notice that they're not just telling us what n is, they just want us to leave n in the formula. So find a formula, we don't need our answer to be a number. If you like writing lists, feel free to write one. What's our U of 1?
No.
What's our R? What put R? Did someone say the R? Close? And that's what I would say by mistake.
Is it negative a third?
Negative a third, yeah. Yeah, so double check. That divide by that, that divide by that. Yep, that's a good point. You can easily think negative 3. It's negative a third.
And
0.3
you don't know it.
Yeah, exactly. We don't know what n is. So they just want us to find a formula.
What happens in law?
Yeah. Use n in your formula. So it's S of n. They're not telling us what n is. U of 1. You might want to write nice and big. And brackets within brackets. I would suggest put the negative a third in a bracket.
Oh yeah, I would put my name with something.
Yeah, I would suggest it, like, because it looks a bit awkward without. And r minus 1 is, what was it again? 1 minus negative a third. Oops, what did I do wrong there?
You have to put it in a bracket.
You
The
could,
and
yeah.
also it's,
Yeah.
is it negative a third? So
Yeah.
that's 1.
R minus 1, isn't it?
Yeah, so negative a third is subtracted.
Yeah. Sorry, yeah. I'm thinking of the other version. No, 1 minus r. Thank you. Yeah, because we're using r minus 1. Is that correct? Yeah, we are. R minus 1. Yeah, good. So negative a third minus 1. We're not using the 1 minus r version of the formula. If you wanted to, we could take it a little bit further and simplify it a bit. They don't say a simplified formula, but we're going to be perfectionists and try to simplify it a bit. So what's negative a third minus 1?
Negative 1.3.
Recurring, or as a fraction?
1.333.
Yep. Which as a fraction is?
Negative 1 and negative 3 over 2.
I'm hearing a lot of,
1/3.
yeah, I'm hearing lots of the correct answer. Negative 1 1/3, or you could say negative 4 thirds. I've heard lots of different versions, they're all correct. You could have said -1 1/3, -1.3 recurring, but you'd have to have the recurring sign is fine. -4/3. Do you tend to find in IB it's nice to have improper fractions because they're a bit less awkward than in terms of math. And when you're dividing by a fraction is the same as multiplying by its reciprocal. Good, yeah. So dividing by a fraction is the same as multiplying by its reciprocal.
Oh, so we have to
So we could say
4/3. Can't we just flip them? Like put that on the top and put the denominator as the numerator and numerator as the denominator? Or
yeah, you could times by 3, divide by 4, yeah. Yeah, so you could just put a 3 up here. That works?
Can we turn the brackets on the top?
Yeah, and we can do that too, yeah. So that would be allowed, yeah.
-3n for 9 times -1/3.
The exponent's awkward, yeah. This comes first before subtract according to BEDMath. Is that what you're asking? So timesing by, so then we're basically, it's all of this multiplied by -3/4.
So what if you just the top simplify to -3 to the power of n minus 9?
wait,
Oh, wait. Sorry, yep, I hear your question. I just realised I made a boo-boo. I
I
forgot
don't
to
even
put,
know what that's not.
it's a bracket within a bracket.
Wait, so you missed the linear what I said?
Yeah, you could expand into there as well. That's also okay, but but which is another way of simplifying, but this is also okay. Like you could. So what we've done is we've multiplied by the reciprocal. So multiply by the reciprocal.
So you multiply by 4/3?
Yeah.
No, to the power of 4/3?
Oh, multiplied by the reciprocal. So -3/4.
So you multiplied the bottom. Wait, can you show how you did it then? Didn't you like kind of?
Yeah. So what I've done is I've rewritten the numerator, and I've just multiplied the entire numerator by the reciprocal of -4/3. So dividing by 4/3 is the same as timesing all of this by -3/4. So this all divided by that is the same as that multiplied by the reciprocal. So that little thing, so that little reciprocal I've popped here and times it by the whole numerator. They might be fine with that. So sometimes in exams they say a formula, they're fine with the unsimplified version, but if they did want you to take it a step further, that's something you could do. And you could, as Grace said, continue to take it further.
Wait, okay, so if we just expanded the first top bracket,
Yeah, that
so
one.
would it simplify to -3 to the power of n minus 9?
Oh, the 9 would have to be multiplied by that term as well. You'd have to do 9 times that, and then 9 times that.
Yes.
Which in a way is like even less simple than that version. Like that version looks a bit more simple than when you expanded it. Because once you've expanded it, you're still just left with 9 brackets -1/3 to the n minus 9, which is just as simple as doing it like that. Like when you expand it, you'll be left with 9 brackets -1/3 to the n minus 9, which in a way is almost as simple as simplified and elegant looking as that. So it's not wrong. That wouldn't be wrong, but it wouldn't be totally necessary. But so no need to erase it if you did that. You could maybe take it further, one more step. You could potentially just do this times that, -3/4 times 9. Yeah, so then, so what's -3/4 times 9?
27 over 4, whatever that
Yeah, that's good. Over 4. And then, looking pretty messy, so just showing you what's possible in terms of, and then all of this is still in there. Oh, why did I put the 9 again? Sorry. Because that's being times by 9. Then it's -1/3. Something had to happen.
Yeah.
There you go. Oh, that's why. It's uncalibrated. It does not want to go further. That's meant to be perfect. Bracket
9. Just like.
So just showing you that it is possible to simplify it. Like, and to be honest, if it just said write a formula, they might be fine with that. But imagine the question was show that it simplifies to this. Just showing you that you could do all those kind of things, yeah.
That's what I mean.
Yeah, let's find this formula. What's that?
Miss Fernandez,
Yes?
thank you. I had a question.
Yeah.
I just come to you after classes for me for like maybe
Oh, this one? Yeah. So this could have been fine, but we were just saying, imagine they wanted you to take it further and say it simplified as much as possible, just showing you that you could potentially do that. Because that negative a third minus 1 becomes negative 4/3. And then remember when you divide by a fraction, it's the same as multiplying by its reciprocal. So I just took that, and instead of dividing by that, I took that and multiplied it by this upside down, which became that.
Where is
And
it?
we just pointed out you could then multiply that in. And this is considered pretty simplified. But if they didn't really require you to simplify it, you could have just done that. So that would have been pretty tough to walk in on. This is a nice straightforward one. Find the sum of the first 12 terms. I just wanted to give you some straightforward ones because the questions, this formula is a bit tricky enough as it is. So quite often you do get nice straightforward questions with this formula because the formula itself is an awkward formula to study. What's our U of 1?
24.
Cool, thank you. What's our common ratio? Is it 2? So a half, yeah, good. So a half or 0.5 you could have said. What's our n? 12. Yeah, boring. Putting the 12 again, I should have given you a different one. They want the sum. So they want the s of n, or you can write s of 12 equals. Just practicing subbing into this awkward formula. So the sum of 12, u of 1, 24, brackets, r to the power of n. If you want, you can write a half, or you can write 0.5, because that does become a finite decimal. So you can write a half to the power of n, or you can put 0.5 to the power of 12. That might be easy to put in your calculator. Minus 1 all over r minus 1. So 0.5 minus 1. It's fine if you put a half instead, but then you would have to put a type of fraction inside a fraction.
A half to the power of 7.
So a clue is our answer is going to be a number less than 100.
It is?
And we'll have to round it to 3 sig figs. Unless it's a finite decimal, if it does become like something 0.05. So yeah, let's practice throwing it in our little calculators. Krista, do you have a calculator?
Yeah.
You do, yay! Excellent, good.
Eli didn't have one.
Yeah, but ages ago, I remember you said you had to buy one. Yeah, it was a long time ago though. And I just realised I forgot to ask you if you've got one yet. Next month? Or, what's that? Oh, Amazon, or you're talking about the graphing calculators? Yeah. So they are actually a requirement, and soon we're going to get to the point where you're forced to use it because you have to graph. Yeah, so you'll need one pretty soon. You'll have been able to survive until now without one. Because soon we'll be graphing and solving by graphing. Did you get 48 point something? Yeah, let's write out the unrounded first. 48 point. Is it like that?
I got 47.
Yeah, 47.988.
So
That's so different.
that's
47.988.
Yeah.
Yeah, that's good. Write it unrounded first and then round to 3 sig figs. Because it doesn't have an end, does it? So we'll round to 3 sig figs. Right, always write the unrounded. Yeah, cool. 48.0. So that's good that you've noticed that. Always write the unrounded first. And then, so if you make a mistake in the rounding, the examiner can still tick that as being right. So always write the unrounded first is a big tip. So I'll always be having to nag people. That was the same in CIE though, wasn't it? You always had to write the unrounded first and then round to 3 sig figs. Is anyone taking that down? Tell me if it's moving too fast. No problem if you want to go back. And one more page front and back and then we're done. No one's writing this anymore? Bit weird, yeah. So now we'll get on to some trickier ones. Okay, this one I think I thought was reasonably long, so I gave you a whole page to do it. Find the sum of the sequence of numbers But hints, to find the sum, you need the u of 1, which we've got. You need n, which we don't have. So what's our u of 1? I guess I want to stop asking this. Okay. What is our common ratio? A half. Good, yeah, half or 0.5. 0.5 is a finite decimal. I wouldn't, if it was a third, I wouldn't write 0.3 because of course it's not 0.3, it's 0.3 recurring. But if it's a finite decimal, like a quarter or a half, feel free to turn it into a decimal then. Oh, right, if you want to practice your fractions, leave it as a half. The thing is, we don't know what n is, so we can't calculate the sum. So in order to do that, as I've kind of given you a hint, we need to find n first. So let's do that on the side.
To find n first.
Yeah, we're going to need to find n first. What n corresponds to the last term?
What n?
Yeah, what is the n value for that final term?
1. 5 or 12.
5, 12. So remember there's a u of n formula for geometric. U of n equals?
U,
Yeah.
R, N,
Yeah. So we're going to apply that. We're going to call this thing 1 over 512. 1 over 512.
That's the last.
Yeah, the last term is good. Last term.
128.
Yeah, good. 128. If you want to, when you're working out, you can put multiply signs. Times 5, 128.
What is log?
Yeah, we're solving for an unknown n, aren't we? What am I doing? 128 times the common ratio, which is 0.5. N minus 1. So that's awkward, isn't it? An awkward one? Good practice of loggy solving. So it's good that you've actually observed that we will need to solve using logs, unfortunately. So before we start to log both sides, we need to deal with the 128. So how do we deal with the 128? Divide it, yep. So divide it off. So 1 over 512. A way of dividing something off is to multiply it into the numerator. Do you want to save space on your page? It's not the denominator. So I said numerator, didn't I? Thanks, Grace. Yeah, if you multiply it into the denominator, that's another way of dividing. Yeah, so 1 over 5, it's okay if you wrote 1 over 512 and then you wrote the divide sign, 128, just showing you that this is actually possible. Equals 0.5 to the power of n minus 1. Feel free to work out what that number is if you want. Does anyone want to do that? What's 512 divided by... Sorry, 512 times 128? That's pretty hard. Notice that there are also powers of 2. This might end up being something we can do non-calc, just out of interest. Do pretty nasty non-calc. 512 out of interest is the same as 2 to the power of?
What?
2 to the power of 5 is 32. And then 32 times 2?
64.
64 times 2?
128.
So that's 2 to the power of 7. 128 times 2?
256.
Yeah, something like that. 256, I think. That's right, yeah. So that 2 to the 8 is 256. And then 256 times 2?
5. Wow.
Yeah, so that's 2 to the 9.
What are you doing?
Wait, what is happening?
Just showing you that it is, I just picked up that these are also powers
But
of
how can
2.
we just
So we have to
divide
like
by
No.
divided by
Or make life easier?
If it was non-calc, we'd have to do that.
Would it be non-calc?
Be pretty mean. That'd be a very mean, that would be a really mean non-calc. So leave yours there, and then, but there's space underneath, you can do the alternative. We'll do, just to show you the non-calc version, equals the same as 1/2 to the power of n minus 1. So I'm showing you again like how bad it could possibly be. What's 2 to the 9 times 2 to the 7?
2 to the 16th.
Yay, good. Add the exponents and keep the same base. Well, this is, we might not even have to use logs.
Wait,
1/2 is the same as, yeah?
How come we just didn't do 1 divided by 15 divided by 128?
Oh, that one? Yeah, that's also okay. But if we had calculator, I'm showing you if this was really horrible,
I
really
did
horrible
1 divided
non-calc.
by 50 divided by 128, and you got 0.0000152 something.
15, do you mean like 512? Maybe, yeah, you get a tiny number. Yeah, yeah, so it's a tiny number. I just picked up that it is even possible to do this non-calc. 1/2 is the same as 2 to the power of something.
2 to the power of 0.5.
Close? Yep, really close. 1/2 is the same as 2 to the power of. Back to
Oh,
exponent
negative
laws.
1.
Yeah, good. Exponent laws. And let's find it.
And then you just multiply them in or distribute
Yeah.
the things in.
You could do that, yep. Notice also, how can we express this as a base 2? Just like what, just exactly like what Krista did to that one. Yeah, hold on. Equals 2 to the power of, would you agree?
Negative 1 and
Yep.
plus 1.
Well done, yep. So
And
see
then
what
you can
Krista's
do
doing
that
there?
again.
She's doing that kind of thing.
And then can't you, isn't it like 16 subtract 1 and plus 1?
Yeah, that's right. Because you've got the same base, you can equate the indices.
Can you explain?
So then it's 2 equals 16
Yeah.
subtract n plus 1.
Wait, but you have to multiply the two. Never mind.
Remember like something like x to the power of negative n equals 1 over x to the n, negative exponent laws. So Isabella, do you remember this? Like x to the power of negative n is the same as 1 over x to the n. So what Krista's done is she saw, okay, 1/2, that's 1 over 2 to the 1. You can do the reverse. You can go from that back to that. And that made it 2 to the power of something. And then same with this can come up to the top.
And then you just multiply negative 1 and yes, I mean.
Yeah, and notice we've got the same base. So technically we can equate the indices.
Okay.
You do actually, you will be getting yucky problems like this in this stuff too.
I could have gone to test, I just wouldn't have a clue what to do.
That's pretty tough.
Yeah,
Yeah, and now it's just a solving one. Yeah, so you can equate the indices. So now what we can do is, if it helps, you might want to write equate the indices. Equate the indices or equate the expression.
No way, we got it, guys. We should feel accomplished.
That's pretty tough.
I know, but we should feel really accomplished.
It's pretty tough, this one, indeed.
Oh,
So some, yeah, then you solve it. It's just the way I wrote it looks a bit weird though, doesn't it? So I'm going to rewrite it. It looks funny.
What does it mean to be creepy?
So it's n 17.
That's a word.
Okay, so it just sounds fancy. Make the indices, because the bases are the same, so technically that index must be the same as that index, because you've got the same base, and there's an equal sign here. So technically they must be the same as each other.
Does it say no, Chuck Norris can divide by zero?
So therefore n equals 1 plus 16. Would you agree?
Yeah. Wait,
How horrible is that?
I didn't do that.
She just did it a different way. You could just
Oh,
subtract
yeah.
1 and subtract 1. So that's 500.
Yeah, exactly. Yeah, you could have subtracted 1 from both sides instead and divided by negative 1. That's okay.
She wants to be a little fancy outside.
And this little negative exponent law is a lot to do with those steps, if it helps to write that one down. Again, showing you like how this was with calculator, this would have been easy. So no problem if this would have been with calculator. I just picked up, this could be possibly done without, so let's do it without. Again, to show you how awful it can be. Powers of 2, so isn't that amazing? Like by the end of IB2, you'll see something like this and you'll go, oh, that's 2 to the power of 9. And oh, that's 2 to the power of 7. Yeah, that'll be like, oh, how easy is that? Yeah, so end of IB2, something like that would be super easy for you. Right now, it would seem really hard. And now, now we need to just find the sum. Now find the sum of 17 terms. So all that work was just to find the n, and now we just use the sum formula. So sum of 17 terms, s of 17 equals u of 1, which is 128. U of 1, r, which is what again? 0.5 to the power of n, which is 17. Minus 1 over 0.5 minus 1. You could totally do that with calculator if you like. We might make you do that one non-calc. You're welcome to try it, but that would be pretty mean. This is one that's very commonly added into a calculator. Like 0.5 to the power of 17 is a bit rough. But that's 2 to the 7, and that's 2 to the negative 1, 2 to the negative
Could we
17.
just cancel them out in a way? And then it'll be never mind.
You could do a bit of cancelling if you wanted. Yeah, 0.5 minus 1 is negative 0.5. And then that divided by negative 0.5 is negative 64. So you're welcome to try it non-calc if you like. But I figured I've exhausted your non-calc enough. A clue is you get a number less than between 200 and 300, in case you've got a number and you're not sure. 256.0? I got 256 exactly. Didn't
I
you?
did it.
I got 255.99.
You guys must be right.
What's that point zero?
So I just
Yeah.
two
rounded
I
it.
rounded it up.
Oh,
You got 2.5?
okay.
Yeah.
That's
I
interesting.
got that too.
Oh, you guys must be right. So it's probably because I rounded and I didn't
Yeah,
make note if I'd
256.
rounded. Yeah, yeah, it's a 366. Yep. So you might want to write the unrounded to begin with, and then round it. And 256, just to practice your powers of 2. 256 is 2 to the power of.
Ooh.
Wow.
Close. 512 was 2 to the 9.
2 to the 6.
It was one.
Close.
2 to the 8.
2 to the 8.
5.
2 to the 8 was right.
It was 2 to the
Because it's half of 512. And that's 2 to the 9.
And that's 128 times 2.
And that one's 2 to the 7. So that one's 2 to the 8, just out of interest. Good thing you'll soon become really aware of powers of 2 and powers of 3. A little bit of powers of 5 as well. So you're going to become really familiar with them very soon. So that was very hard. Here's 2 more, maybe a bit more straight up ones. A geometric sequence. This previous one would have been easy if it was with calc. The fact that we just tried it non-calc made it harder. Yeah. A geometric sequence has the first term 6 and a common ratio of 2. The sum of the first n terms is this thing. We need to find n. We might be getting to the point where we have to solve by graphing as well. Because as in, like, it's pretty hard to solve. U of 1 is 6. Our r equals 2. We don't know what n is.
N is
That's it, yeah, exactly. And the sum is that. So we know what the sum is. So a big sum formula. So if you want to write the sum formula, it might be helpful. If it was non-calculable. There might be one where, and I would see this as a classic example of where they maybe want you to solve by graphing. So just reminding you of what the formula was to begin with, so you know what goes where. That number goes here.
How do we solve by graphing?
You plug this into y1, and this stuff with the thing subbed into y2, and you find you graph them both, and you find the point of intersection.
What if they intersect more than once?
That's a good point. If one intersects down in the negatives, then you reject that answer.
Wait, so what if it doesn't?
I'll go the first one in the positive.
The first one.
Yeah, the first one in the positive, yeah.
you put n in one and then you put that
Yeah.
on another.
Yeah, with the numbers up in. So Sn, of course, so y1 would be 786, 426. You might want to practice graphing this. So in your y1, grab your little graphing calculators. In your, like you go y equals. In y1, that's your first line. It's just a horizontal line that cuts through that number on the y-axis. And the second one, you'll be putting all this other business. 6 brackets, 2 to the power of n. N, you'll put x instead. Minus 1. You'll need to do your alpha y equals to enter this function. R minus 1 is just 2 minus 1. So to be honest, it's just 2. So, 1. So you could just enter that, really. But if you're in doubt, just put it in like that.
And can we do the non-calculate?
Probably good because you can divide off 6, can't you? And add 1. And you might find that it's a nice number. It's a power of 2.
Because it's negative one, we just, because it's one, you just erase that, you mean.
Mm.
And divide by 6.
Commonly these are done by graphing. But yeah, feel free to try.
So they're called logs and nonsense.
7, 8, 6. Some log nonsense, yes. 6. 2 minus 1. Because that just becomes 1. What's that number divided by 6?
13,000, then 131,000 and 71.
Oh, is it? Oh, we might as well get a nice power of 2.
Yeah, we won't probably.
Then we've got to add 1 to both sides.
I graphed it and it didn't show up.
Oh, and you remember your window settings?
Yeah.
So your window settings, when you go, your Y-max is going to have to be bigger than that number because that's a horizontal line that cuts through that. So you'll have to put in something like 900,000 for your Y-max. 900,000 is a good idea for your Y-max. Your N could be a really big number, so maybe make sure your X-axis goes up to 100 or something.
Hey, what does n equal to? The number of terms?
Yeah, the number of terms. So which term number, if you added all the terms together and you got a sum of this, how many terms would you have added together to get that sum? Yeah. What it was. So then if you were doing them, calculator, go 1, 3, 2. No, what am I doing? 1, 3, 1, 0, 7, 2. And then you have to log some business, unless you happen to get a nice power of 2. If that's a power of 2. We should get a whole number, so that must be a power of 2. A really big one though. Much bigger than 2 to the 9. So have you made your Y-max really high? So let's see your window. Oh, no, yes, I did. It's probably because you're fully zoomed out. You only need your Y-max. So if you graph it, your Y-max, because this line here is going to be a line through that number. So you want to go up to here. And normally, to be honest, they don't really go beyond ends of 100 or 200. So feel free to make your Y-max, your X-max something like 100. 100? Yeah. And if you can't see it, then try 200. X-min just somewhere below here. Like you want your Y-min, like even from 0. You can make those 0 if you want. I tend to put in -10. Y-min and X-min as -10.
Y-min. Can we do the non-calculator?
Probably -10. What did you put, Paige? Yeah, -10, -20. So you could just see that. Like you don't need to really see that here. So you could just make it something like -10. I tend not to do 0 or else you can't see your axes at all. And then you'll probably find it's a, yeah, it might intersect. And they want to know what is the x coordinate of that little intersection point. 17. That's boring. We got the same answer as the last one. Oh, supposedly get 17. This one? Yeah, at this point, that's a bit full on to realise that that's a power of 2. So it turns out it's 2 to the 17. So we would suggest graphing. What you would want to do is, I tend to graph the original stuff. I tend to graph that in Y1, graph that in Y2. You need to adjust your windows so that your Y-max is above this number, like 900. The ends tend to not go beyond 100 or 200 on the x-axis. And then you would have to find the intersection, second calc intersect. Yeah, pretty intense. That little last one there, if you want, we can... Yeah, they wanted the N. It just turned out it happened to be the same answer as the previous N, but that's just a weird coincidence. It's lunchtime, you guys can go now if you like. That was a lot to do. Don't forget to, before next lesson, be doing some of 6B and 6C. I'll come around and I'll spy, and then show me so then I don't have to feel worried.